Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, okay, we are all in a new age generation, and unless we start with some commercial, we don't get entertained sufficiently. So, let me start with a commercial. Okay. So, this is best paper award winner, the idea that I am going to discuss with you in IWSEC. It was one of the premier conferences in cryptography. And my students, Sharmila Devaselvi and Sri Vivek, they are the PhD students. Both of them have submitted their thesis, and Vivek is almost got the degree, and Sharmila is waiting for the degree. And it is their work, and then this got the best student paper award, and the commercial part is over. And now let us start with the content. What is digital signature? You have seen physical signature, physical signed document. There is a sheet of paper, and the bottom you have some signature, and that is authenticating or binding the signer with the document. So the point is that it is a kind of a commitment. Later on he can't deny, saying that this is not my signature or something like that. And at the same time, we need a safeguard for the signer also. If someone could produce a document with signature just like mine, saying that I owe him $1 million, and then claiming that he owes, I might not have even seen him, but still if he could produce something, it is forgery. Okay. So the document which somebody could generate without the signer is a forgery, and obviously forgery should be impossible. And so in our real world, in the paper document signature, we have several safeguards on, so there is a witness, and all kinds of things are there to ensure that the genuineness and so on. But still, theoretically it is possible to generate a forged document, okay, perfectly looking like signature if somebody signs, and then if they could create something like that, and if everybody would believe that it is indeed a signature, okay, signed document by you, and they will swear that you must have generated it and so on, right? Therefore, the forgery has to be avoided, etc. in the real world, in the paper document, and we are going to have the analog of that in the digital world, okay? So in the digital world, we can imagine the document or the message as a bit stream. Message is a bit stream. And this message is to be signed, and a signed document is to be produced. Signed document is also, you can imagine, as a bit stream. Okay. And there is a signer. So there is a signer. We assume that we are working in what is known as public key cryptography. So what we mean by public key cryptography is, signer has got a public key and a secret key. Public key is made public, everyone knows this, the whole world knows about this. Secret key is known only to him. Okay. The public key and secret key will be a complementing pair, so that the effect created by one can be undone only with the other. Okay. If you encrypt with one, you can decrypt with the other, only with the other. That's the kind of a mathematical property they have, public key and secret key. Okay. So public key and secret key can also be considered as a bit streams. We will make it a little more concrete with our example. So basically we have a public key and secret key for a signer. So how the signer is going to sign the or generate a document? There is a signing algorithm. So this signing algorithm will take the message as an input, then his secret key, the user's secret key, and possibly some randomness, okay, some random value, and then it will produce a signature. This sigma is the notation for the output, which is a signature. And the signature and the message will be given to whoever it is. Suppose I borrowed 50 lakhs from you. Then I will produce a document saying that I owe you 50 lakhs, and then my signature signed a document. Both I will give you. So you will have the statement in plain and the signature. So what goes to the receiver is the sigma and m. Both will be given to the receiver. So signer gives to somebody the signed document. Okay. There are two parties here, one receiver and one signer. We need protection for both. The first one is non-repudiation. Non-repudiation means I borrow money from you, I give you signed document, and then little later I pretend as if I didn't sign it. So I refuse, saying that I have nothing to do with this. He brings me some statement as if it is my, I have nothing to do with it. If I claim, I am refusing this. It should not happen. My scheme must be robust that I should not be able to refute later. Once I produce, the binding, okay, is so authentic that I should not refute later. Okay, that guarantee should be there. Only then the other party will trust this signature scheme and the signature. The second one is the protection for the signer. That is the forgery, which I have told you. Somebody should not simply create a document without my involvement and claim that here is the document signed by me. So for example, you and I might not have met at all. Suddenly you are producing a document saying that you owe me 50 lakhs rupees and here is your signed document. Then I will be completely in a loss. So it should not also happen. Okay. So how do we mathematically formalize this? We formalize this in the following way. For every signature scheme, there is a verification algorithm. This verify algorithm will take the signed document and the message, and not only that, for the corresponding secret key there is a public key, because this is a signer by, let us say A is the signer who has produced, and A's secret key was used while generating the signed document by A. It is done in-house by him. It is not visible to anybody because he is using his secret key and it should not be done. So A will prepare the signed document and then give it to you. It is done in his private resource. Verification, on the other hand, is public. Anyone can verify. In fact, anyone should be able to verify. In case of a dispute, there is a third party who is going to verify this. So this verify algorithm will take the signed document, message, and the public key of A, and then there is a Boolean result, yes or no. Okay? If the verify says yes, this is a document, signed document on this message by this user. There's no question of this fellow backing out. Non-repudiation is taken care because his public key is used in the verification process. We also have a mathematical property that whatever was done by that secret key can only be undone or verified only by the public key. Under that assumption, if I use pKa, sigma and m, and if verify gives yes, okay, then it is a document generated by A on the message M. That is it. Okay. On the other hand, if it says no, that will reject the claim. So much like you might say, you might produce some document, I see that there is a rubbing mark and there is something, this is not my like signature, and somebody also verifies and then rejects, saying that this is a useless forged document, I can't authorize it and all. Same way, the verification algorithm may say no. So what is the forgery here? Forgery is the act of generating for some message M a sigma which on this pKa would produce the answer yes. Notice that this is a public key, this is available. I know the public key of Bill Gates. Okay, and I know the message. I owe Pandurangan $1 million. I know the message also. Suppose I could generate a sigma which I give to the verification algorithm and the message and the public key, and if it gives the answer yes, now I can go to the court of law and claim my money. Because the law will check that and it verifies, then it will say, yes, Bill Gates, yes, Mr. Gates, you have borrowed money from him one day and you have given the signed document, pay him back, it would say, right? So what is a forgery? Forgery is the act of creating for a sigma for some message with respect to a user. It should be impossible. So if you want to have a guarantee that the forgery is impossible, what you have to actually prove is the following. It is not possible to fool the verification algorithm. This verifying algorithm cannot be fooled. Okay? In other words, you have to argue for the impossibility. That is exactly what you have to do. So if at all, therefore, what is a signature scheme? Signature scheme is a pair of algorithms. A signing algorithm and a verification algorithm. Signing algorithm is used to produce a signature. Verification algorithm gives the validity of it. Forgery means without the knowledge of the secret key, only with the public knowledge, I am able to produce a triplet which is fooling the verification algorithm. Much like in the real world, I am producing a document which has got perfect replica of my signature, let's say, then that's a forged document, but then no one could distinguish, means it is accepted as a correct document. The same way, if you could manage to fool the verification algorithm, it is considered as a one, but that's a forgery. Your scheme must be robust enough that nobody should be able to fool the verification algorithm and produce something like this. That is the goal. So when you are trying to design a signature scheme, you must make sure that it is impossible for you to fool the verification algorithm. That's the goal. Okay? That is the goal of the designing a signature algorithm. That is the cryptographic goal. In general, in cryptography, there are crypto functionality like encryption, decryption, and other things. Encryption maintains the confidentiality. Nobody other than the person to whom it is intended should be able to decrypt. That is the security property you want on the message. Okay. Here, message is open because it goes to public. He can show to anyone, yes, here is a document signed by him on this message. Anyone can verify. These are all public. What is important is the binding. Okay. Only this person would have generated this is important here. So in signature, it is not the confidentiality, but the binding of the individual with the message through that signature is the most important thing. Therefore, we will focus on the forgery or unforgeability. How do we show the impossibility in mathematics? In mathematics, we have a lot of techniques. Proof by contradiction and variety of techniques are available to show the impossibility of certain result. In computer science, okay, the impossibility or the degree of difficulty of certain things are done through reduction technique. And that is exactly what we are going to do here. So, the topic that I am going to discuss is formally called as provable security. Provable security. In provable security, in fact, how the security property or cryptography properties were all shown in the early days or in the unsophisticated days. They will say that combinatorial argument, they will count the number of possible ways in which it can be done, and that runs into trillion. Therefore, it is not possible for someone to break, etc. kind of a exhaustive count based argument. That is completely unscientific. For example, even if you have 8 characters, your password for your Yahoo or Gmail or whatever it is, has got trillions and trillions of combinations. Okay? But nobody tries to check, or if somebody wants to break your password, he's not going to check like, is A is password. If not, is A, B is password. If not, that's not the way somebody goes to hack your account. Well, if that is the way he has taken, then it may take several years, 100 years. But they could crack your password or anybody's password in 10 minutes. Okay, low entropy and other things are used for cracking the password. Therefore, almost anybody's password people can crack in 10 minutes. Therefore, you clearly see that this combinatorial counting argument saying that the total number of scenario in the context is running into trillions, therefore exhaustive attempt is going to take several hundred years, therefore my system is secure, is completely ridiculous argument. And any system that was built on such assumptions were all completely broken. So we need a formal way to do that. So provable security is a more scientific, rational way of arguing on the security properties of crypto primitives, whether it is an encryption scheme or hash function or signature schemes or any other cryptographic primitives, commitment, zero knowledge protocols, take anything, you have to now formally prove. How do you prove this formally? Now, much like NP completeness, we are going to do the basic thing of reduction or relating something to a hard problem. Suppose I have a situation, suppose I have a problem in my hand, a hard problem in my hand, okay, which I know, right, is not solvable in polynomial time. Okay. Now, if there is a forger exists for this, I will produce a polynomial time solution for that problem. In that case, the contradicting scenario here shows that such a forger cannot exist. If a forger exists, that leads to a polynomial time solution, but we know that that problem is not solvable in polynomial time. Therefore, such a forger cannot exist and such a forgery to my scheme cannot be produced, and all follow by implication. Therefore, the whole art is relating degree of difficulty of solvability of a hard problem to the forgeability of a scheme in hand. If we could do that, that shows the robustness of the scheme. That is the fundamental technique. But this technique is to be used in a much better way, in a completely different way than what you show in NP completeness. Okay, the techniques are very different. Reduction is the principle, but the way in which you apply is very different. That is because the scenario is a bit different here. Okay, so first let me start with some hard problem or number theory reference problem, which I am going to use to show the hardness of my scheme. I need three basic mathematical ingredients before I begin the description of my scheme. So I will give the introduction to these three math basics, and from then onwards we can get into the scheme and the details. All right. So what is the first thing that I require? I need a hard problem. So I'm going to straight away go to the specific hard problem that I'm going to use for my scheme. Therefore, without getting into too much of number theory and other things, directly let me go to the statement of the hard problem. Okay, so here I'm going to use a little bit of number theory, and you know, given a prime number p, z star p, the set of all numbers which are relatively prime to it form a group. In fact, it is forming a cyclic group, and there is a generator which is going, whose powers will generate all the items of this group. So even if you are not familiar with this kind of a thing, let me give a simple example. Let us consider the prime number 11, and if you consider 2, 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8, 2 power 4 is 5, 2 power 6 is 10, 2 power 5. Another, when I multiply by 2, here I also multiply by 2, and then I take modulo 11. So when I take the modulo 11, because I am in the world z star p, for example 8 times 2 is 16, and when you take modulo 2 you get 5. And 2 power 7 is 20, this is 9, and 2 power 8 is 7, 2 power 9 is 3. I made some mistake somewhere. Let me see, where did I do? 2 power 6 is this, and 2 power 7 is this, and 2 power 8 is this, and 2 power 9 is 6, and 2 power 10 is 1. Okay, so there it ends. Okay, and once you get this one, Fermat's little theorem says that is going to happen. Okay, so don't worry about it. Now you can see the powers of 2 enumerate everybody. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Everybody is sitting over here. So all numbers from 1 to 10 are generated by the powers of 2. 2 is said to be a generator of this group. Okay. When you have G as a generator for a group, any element Y belonging to G, if G is a generator, suppose G belongs to G is a generator, there exists a power of G which is equal to Y. Y equal to G power X for some X, some integer X. For example, here if you consider 9 and G being 2, and this is 2 power 6. Okay, of course we are in the mod 11 world, 9 equal to G. So much like the logarithms that you have, we have what is known as the discrete logarithm. This is spoken in the context of modulo world, so this is called the discrete logarithm. The discrete logarithm is with respect to the generator. So now the X is almost like log Y to the base G. I will continue to use the notation log Y to the base G. This is equal to X, except that it is in the modulo world 11, to show that this is a discrete log and this is not a continuous logarithm, and so on. Okay. Now, given the prime number P like this, and given a generator G, and given a Y, finding this X is called the discrete log problem. Okay? To our utter embarrassment for the human race, nobody could find a polynomial time solution for this, and there is no polynomial time, randomized polynomial time algorithm is also available for this. And what is adding more spice to the story is we do not have the proof of NP completeness or NP hardness either for this. We do not know exactly the complexity status of this. We do not know whether it is an easy problem or a hard problem, but there is more evidence that it is a hard problem. Lot of attempts have been done. Nobody could solve it. So I'm going to make an assumption. This is called discrete log assumption. Discrete log assumption is there is no polynomial time randomized algorithm that is going to produce an answer for the discrete log problem. This is the plain English. There is a formal way to say that. In randomized algorithm, if the probability of getting the correct output is negligibly small, unreasonably small, it is as good as a failure of that algorithm, and that is the formal notation we will use to say our inability to solve the discrete log problem. Okay? In other words, for any polynomial time randomized algorithm, A, you give Y to it, you give the generator G to it, you give the prime P to it, the probability that the A is outputting X, where X is the discrete log, okay, is going to be extremely small, negligibly small, exponentially small. Okay, say if it is something like less than 1 by P, whether P is a very large number, very, very large prime number, something like this, unreasonably small. For any polynomial time randomized algorithm, this is the probability of success. In other words, it can't do anything better than guessing, right? No algorithm is able to find a pattern or find a calculated shortcut to actually output it, because every polynomial time algorithm is failing miserably. And therefore, this is called assumption, discrete log assumption. So discrete log assumption is one assumption that I need. So this is one of the number theoretic reference problem. I need one more number theoretic reference problem which is close to it, and with that I will wind up the hard problem part of my discussion. The second problem that we are facing extremely difficult, yeah. Huh? No. This is, there is the coin tosses involved here are for the generator and for Y. Yes, it has got its own coin tosses also. It's a randomized polynomial time. Yes, it is a function of all, and no matter what you use, you are not able to get it done other than, or not much better than guessing, let us say. Then that is the assumption we are going to make. To express our inability to solve this problem in polynomial time, this is the way to formalize that notation. Okay. So this is called a discrete log assumption. We need one more hard problem and its assumption. Okay. And this is called Computational Diffie-Hellman assumption, CDH assumption. Computational Diffie-Hellman problem is a problem based on which the first key exchange algorithm in cryptography was reported. In fact, this has opened up the modern gateway for modern cryptography, and this is considered as the starting point of modern cryptography. Okay, this particular problem and the crypto things which they did with this is considered, there is an era before it, era after it. That's the kind of a problem is the Diffie and Hellman are the people who have used this problem for key exchange. We will not go into that. I will specify only the mathematical problem related to that. Suppose I give you, let us again continue with this kind of a cyclic group. Let me have a generator G. Suppose I give you G power A for some A. I will not give you A. I won't tell you what A is. I will give you only G power A. Like without telling you 6, I will give you 2 and I will give you 9. Okay. And then I will give, I won't tell you what 3 is, but I will give you 8. Okay. So given G power A, G power B, okay, generator is given, generator raised to something is given, generator raised to something else is also given. Now your mission is to compute G power AB. All are mod P, or if it is a group computation, abstract group operation, whatever is the group operation, that many times. Okay, take it that way. For our modulo world, assume that modulo the prime number, all the computations are done. So how do you compute this? You have no knowledge of A. Like what will be visible to you is 2, 9 and 8. And now you have to find out 2 power, whatever is the power in which this is raised, and whatever that multiplied G power AB is what you have to find out. Okay. So that is the mission. Nobody could find a polynomial time solution for it, deterministic, randomized. Not only nobody could find it, nobody could ascertain the exact complexity status of these problems. So its degree of difficulty is assumed, and that is called CDH assumption, Computational Diffie-Hellman assumption. So the Computational Diffie-Hellman assumption is the following. Given G, G power A and G power B, output G power AB. This you can't do in polynomial time. That is the CDH assumption. Okay. Now, let us paraphrase our forgeability right with respect to the statement that I have made so far. Okay. Suppose there is a forger exists. What does it mean? He is able to produce a forgery in polynomial time. Suppose I do some more polynomial time computation with the forgery, and then I solve this problem. So my total effort is for forging polynomial time, some more polynomial time labor. On the whole, I have taken polynomial time and I have solved this problem. But that is a contradiction to the assumption that this is hard. Therefore, my scheme cannot be forged. That is how I am going to build my argument. I am going to design a system in such a way that the forging of my system will imply a polynomial time solution for this problem, and since that is not possible, that automatically implies unforgeability of my scheme and the robustness of my scheme. Okay? So that's the plan of things to come. All right? Now, I need only one more ingredient for discussion of my scheme, and this is again a very well known mathematical construct and available in number theory. Okay, and this is a pairing function, okay, bilinear pairing function. So this can also be discussed in a complete black box manner. Absolutely in a black box manner we can talk, although the technical details of each one of them is deeper and then lot more subtle both in practice and theory. I'm going to only describe the third ingredient, namely the bilinear pairing. So the computational Diffie-Hellman assumption is compute this, given this, compute this computation I can't do in polynomial time is the, of course in exponential time you can do. What is the exponential algorithm? It is very simple. Compute g power 1, g power 2, g power 3, g power 4 and so on until you hit g power a, which is this number. Thereby you discover a. Okay? Once you have the a, this fellow you raise it to that power and then you can always get g power ab. So if you give exponential amount of time, I can solve this problem. It's not an unsolvable problem. Only thing is, it is not solvable in polynomial time is the assumption. Okay? Now, the third mathematical ingredient that I need is a bilinear pairing function. Bilinear pairing functions are typically denoted by E, and it works on a G cross G to another target group GT. Usually this will be an additive group and this will be a multiplicative group. But let me tell you how this is going to work. E of xy, this is a bilinear, therefore it is linear in the first parameter, it is a linear in the second parameter also, which means E of x1 plus x2y equal to E of x1y multiplied by E of x2y, where this dot is the operation here and plus is the operation in this group. Okay, this is a fundamental property. By repeated application, you can see that E of axy equal to E of xy power a. Repeated application of it, because it is the same value, is therefore this is one visible property. And another property, it is linear in the second parameter also, which means E of x by equal to E of xy power b. In fact, E of ax by equal to E of bx ay, which is equal to E of xy power ab. Assume that such a function exists and such a function and its implementation is available. Okay, you can buy this. You have bilinear functions and bilinear maps on appropriate groups are available, implementations are available. You can straight away use it for your application, whatever you are working on. Okay, so assume that such a bilinear map or a function is available. That's all I want. But once I have a bilinear map, I can do something really subtle and wonderful. Okay, what is that nice thing that I can do? I can do something related to this computational Diffie-Hellman problem. That problem is called decision Diffie-Hellman problem. The decision Diffie-Hellman problem is this. You are given G, G power A, G power B and an Z. Now all you have to say is whether this Z is G power AB or not. That's all. Yes or no answer only I want. I don't care I don't want you to compute G power AB. You may use some property or some evidence and then you may conclude the answer no, or you may say the answer is indeed yes. That is up to you, what you use and how to determine. That is called the decision Diffie-Hellman problem, where the answer is yes or no, depending on whether this is G power AB or not. Okay? Now, this decision Diffie-Hellman problem can be solved if you have a pairing function defined on your group. How do we do that? Extremely simple. We are going to use the bilinearity property and I am going to demonstrate that in 1 minute. Okay? So, suppose you see that here this is an arbitrary element and this is an arbitrary element. View this as alpha, beta, gamma and delta. Just 4 elements. Okay? This is an arbitrary element. This is G and this is G power A, yet another. But if you look at this B, this is raising G to power B and G power AB is G power A raised to B. So these two later elements are bth power raised to, the first item is here, the second item bth power raised is over here. Okay? So, if I want the last item to be G power AB, I want this property. The first item B power, whatever is the third item is raised with respect to the first power. The same power should have been used to raise the second item to obtain fourth item. I know it's a very long sentence in English, but in bilinear form, it is absolutely easy to explain. Now, you consider E of alpha delta, the first and last item. The E of alpha delta is nothing but E of G power AB, which is equal to E of G power AB by the property that I have told you. Now, E of beta gamma. E of beta gamma, if it were G power A, G power B, E of G power A, G power B, which is equal to E of G power AB. Therefore, this property will hold good. So, when some number is given to you, I can check whether it is G power AB or not. That I can do if I am equipped with a bilinear pairing function. Okay? But I can't, even this is not helpful in finding G power AB. But given G power A, G power B, this is the test. Is E alpha delta equal to E beta gamma? If this holds good for a 4, they are called Diffie-Hellman tuple. If the inequality is there, they are not Diffie-Hellman tuple. Right? When the equality holds good, it is called a Diffie-Hellman tuple. When there is an inequality, it is not a Diffie-Hellman tuple. That decision version I will be able to solve once I am equipped with a pairing function. That is all the maths that you need to know for the time being. You have to know a lot more, but that is little later. Okay? So, to summarize, all we have seen is the following. A digital signature scheme has got a signing algorithm and verification algorithm. Forgery means producing a triplet like this without the help of the secret key, which would fool the verification test or pass the verification test. We are interested in showing the impossibility of such an act, and to show that, we are going to relate the forgeability of the system to the solvability of the efficient forgeability of the system to the efficient solvability of a hard problem. The hard problem that we have targeted is the computational Diffie-Hellman problem in the scheme of things to come. Okay? And in our construction, we are going to use a bilinear map, and that bilinear map is giving us some very interesting advantages. Okay? One last thing that I would require. This is called cryptographically secure hash function. After this description, I am going to talk about a powerful abstraction of this mechanism, and that is the heart of provable security schemes. Okay? So what is a hash function? In data structure, you might have seen hash function as from some domain to a range B. Usually this will be very large. Cardinality of A is much greater than cardinality of B, and we assume some random properties and so on. That is a data structure hash. But cryptographically secure hash function have got a slightly different property. Here also I am going to use a function from A to B where cardinality of A is much larger than B, but I would want the probability of collision to be as least as possible. Okay? Collision is bound to occur. That is because A is greater than B. Okay? By pigeonhole principle, surely there exists a pair such that, okay, h of x equal to h of y. But it should be computationally infeasible for you to find such a pair. Put again in our formal polynomial notation, right? In polynomial time, the probability that you would get a colliding pair is less than or equal to 1 by cardinality of B. Because with probability 1 by cardinality of B, even a random element may be equal to the item you have chosen, right? So the probability should be less than or equal to this. So probability of an algorithm discovering x, y such that h of x equal to h of y should be less than or equal to this. For any polynomial time algorithm, okay, this should happen. Such a function I am looking for. Okay, they are called collision resistant hash function. There are a couple of other interesting hash functions which we use in cryptography. And the interesting point is, it doesn't matter which hash function you use. There are several hash functions available, SHA-3, RIP-MAD, okay? And then there are so many hash functions are available in the market, in the research labs and all over. You can use any of them. It really doesn't matter. The security is depending on this property. Okay, that is the reason why in my specification of the system I will not specify the body of the hash function. I assume that a particular cryptographically secure hash function is available and then give the specification of my signing algorithm. Therefore, my mathematical proof is also going to rely only on this property and not really on the body of the function of hash and what computation it is doing to produce for a given A, how it is producing B. I don't care. I don't have to look into that aspect at all. Very powerful abstraction. Okay? How this abstraction is actually used in the formal provable security models, this is where we get into one of the most interesting and fundamental proof technique tool, and this is called random oracle. Therefore, the proof based on this is called the random oracle model. We have two proof styles. One is called the random oracle model, another is called the standard model. We will not talk about standard model now. We are focusing on the random oracle model. In random oracle model based proof, we are going to look at the properties of the hash function that we use, if at all we use hash function, right? If we use hash function, that hash function's abstraction is going to be used in the following way. Okay? Hey, I am not going to give you the body of the hash function, but in case you want the hash value, I will produce it for you. Okay? So ask me, you want hash of 7? I will give you. Do you want hash of 43? I will give you. Do you want hash of 1,023,000? I will give you. So for any value, I will give you h of x1, h of x2, etc., h of xn. Whatever you ask, I will give you. And it will have this mathematical property. I will ensure that I will have this mathematical property and then I will give it to you. But I will not give the... So you query and you get an answer. That's why it is called the oracle. It is called the random oracle because it is going to work in the following way. Whenever you ask h of x1 and you give x1 to me, what I do is I select a random element from B and then give that is the h of x1. You ask again h of x2. I select a random element from B and then give it to you. Every time I select a random. So what is the probability that a collision would occur? Obviously, it is going to be something like this. Something like this, okay? There are mathematical techniques to make it negligibly small and so on. But the way in which we are going to have the hash function is replaced with a random oracle. I do one small bookkeeping here. What is the bookkeeping here? You have asked me x1, then x2, then x3. Then again, you have asked me x1. Now, if I generate yet another random number and give it as a response, it won't even be a function. Is h of x1 is that value or this value? Therefore, what I will do to safeguard against this anomaly is, I will maintain all the queries that you ask. Okay? I will have a table. If you ask me any query that you have already asked, the same response I will give to you. If you ask a fresh question, I will make a fresh random generator, random item chosen and then give it as a response. This is just to make it the function, make the response set as a function. That's all. Okay? That minor bookkeeping is only to make it into a function. So this is called a random oracle. Every hash function that I use will be replaced with a random oracle in my proof technique, and that is why it is called a random oracle based proof technique. And the random oracle based proof technique, replacing that with such a interaction, is mathematically preserving this property. Therefore, if you actually use some function, whatever I am giving guarantee in my abstract model, hopefully will happen in the real world also when you use a particular hash function in your actual implementation. Okay? So that's the way we are going to model it. Therefore, the ingredients are bilinear pairing function, a mathematically hard reference problem, the hash function, the abstraction of the hash function as random oracle. Once we are ready with this toolbox, we can now go straight away into the system and its specification. So that's what I am going to do now. So let me skip there are several other things which you can, well, the security model, that also I will explain a little later. Here is the basic scheme. Okay? So P is the generator of the group. So G1 is an additive group and G2 is a multiplicative group. This is a bilinear map. This is a generator. And I have two hash functions I am going to use. One hash function is, this LM is the length of the message. Message is a bit stream. The bit stream length is LM. So LM cross G1 to G1. And H2 is LM cross G1 to ZP. So the output of H2 is a number. The output of H1 is a group element. Remember that. Okay? Output of H1 is a group element and the output of H2 is a number. It's an element in ZP. P is a very large prime number. Let's say 1024-bit long prime number. Very, very huge prime number. If you use a prime number like 13 or 23, even a school dropout will break the system. You must use extremely large prime numbers. Okay. Now, here is the key generation algorithm. How is that person defining his public key and secret key? It is very simple. Choose two random numbers from ZP, S1 and S2. And S1P, S2P. Okay? Now, the reason why I have written S1P and S2P is, it is an additive group. In additive group, when you do repeatedly the group operation, the multiple operation will be written like this. Right? That is because A plus A plus A plus A is written as 4A in additive group. If it is a multiplicative group, A dot A dot A dot A is written as A power 4. So if it is a multiplicative group, the convention will be to write in exponent. If it is an additive group, the convention is to write it as a coefficient. Basically, it is a group operation done several times. So the discrete log problem, well, how will the computational Diffie-Hellman problem will look in additive group. In additive group, it will look like this. Given G, or here I have assumed P is the generator. AP, BP, finding ABP is hard. This is how it will look like. The same problem in an additive group, it will look like this. It's only a change in form in which it is presented. So don't be unduly disturbed by that. So it's very simple. Okay, 2 random elements are chosen, and that many times the generator is operated and then obtained 2 group element, and that is all is the public key. So public key and private key are specified. Now signing algorithm and verification algorithm. Okay. So here is the signing algorithm. Very simple. Only few steps. So I'm going to explain the logic behind it. And then here is the verification algorithm. That is also very simple. Okay. So I'm going to explain the signing algorithm. How much time I have? Oh, I have only 10 minutes. No, I have a lot of time. Okay. Yeah, I have 40 minutes. That's good enough to really chop your head off. So I am going to do that. Okay. So here is the signing algorithm. Very simple signing algorithm here. You choose a random number. Take the second public key. Okay. And multiply with the random number that you have chosen. And that is going to give, because this is an element of the group, this is giving, so ym is a group element. So take the message to be signed and the ym that is computed, hash it with h1. Remember, h1 is giving a group element, therefore this is going to give a group element. Multiply that group element r times, or add r times and compute r. So xm is another group element. Ym is a group element. Xm is also a group element. Then again bind xm with m and find h2 now. Now h2 will map this pair to a number. Remember, h2 maps it to a number. So qm is an integer. S1 and S2 are all numbers. Okay. So qm multiplied by S1, the random number multiplied by S2, mod p, this is a number, and dm is a number. Find that number. Okay. Compute this number dm. Notice that this step can be executed only by the person who has a secret key, because S1 and S2 are secret key. This is a signer algorithm. Signing cannot be done by anyone in the world. Signing can be done only by the person who is trying to produce the document. Therefore, signing algorithm will involve secret keys. And here is where the secret keys are involved, and then now the signature is dm and xm. xm is produced here, dm is produced here. These two are considered as the signature of the message m. Therefore, the way to produce a signature is execute this algorithm, produce those two values, one group element, one integer, and then that is going to be the signed document corresponding to m, sigma m. Okay. Now, alright, what is the verification algorithm? This is the verification algorithm. The reason why I want to specify the verification algorithm is the following. The forger is essentially trying to fool this, and your mission is to prove that it is impossible to fool this verification algorithm. Okay. That is the actual mission. So the security of the system depends on the inability of the world to fool this particular algorithm. If anyone can fool this algorithm, this signature scheme is not robust. If no one can fool this algorithm, then the signature scheme is robust. Therefore, pay attention to the verification algorithm. The first thing we are doing is the following. We are computing ym, which is generated in our algorithm through this formula. Okay, this is obvious. The reason is given here. If you go back to one slide, you will realize that why ym is that value, because dm is, oops, I have done something. How do I come out of this? What do I do here? Okay, ym is this. R times P2. So you multiply by P2 so that you get R times P2 here. Subtract from the other end, you will be able to get Ym. And that is what, has it diminished the size? Okay. So that is what this step has done. Now look at the second condition. The second condition is if E of xm P2 equal to E of H1m Ym and Ym. What is this condition? This is simply checking whether the Diffie-Hellman property is satisfied, alpha, beta, gamma, delta, whether the third and fourth element are multiplying with the same value with respect to first and second element. Why? Here is the, you look at the algorithm, you will know that. Ym is the multiple of R times P2, xm is R times multiple of this one. So you put these two values first and second, these two as third and fourth, then third element is R times for some R of this, and the same R is multiplied to use this. So the relation between xm and ym in terms of P2 and hm2 is what is captured in this check. Oh my goodness, this is really irritating. Anyway, so that's all. Don't worry about anything. What all I have done is that these four, that xm and ym are outcome of the multiplication of the same value, but nobody knows what that value is, but still I can verify whether it is the same case. If that is the case, then the values are sane values, otherwise they are insane, rubbish values. Okay, so otherwise it is going to, if this holds, then the signature is valid, otherwise it is going to be invalid. That is all the verification algorithm is going to. Ym is involved and xm is involved, message is involved, and whether they are outcome of the same value, whatever the value, that is not known to anybody, that doesn't matter, verifier doesn't know. The signer might have chosen some R, that R is never passed, but still someone can verify thanks to the availability of the pairing function. Pairing functions power comes here. So although the signer might have used a value that was not even exposed, but still the signature components, are they produced in the same way, are they having right relation, is verified by this condition. That is all, and that finishes the description of the signing algorithm and verification algorithm. Okay, so these are all some formal statements. Let's not worry about it. Yes, question please. How is it? During the transit, we assume that the data is safely transported. We assume that the signed document is properly made available. We will not worry about such errors. Transmission errors and data error and all, we are not looking at it. Only security property we are concentrating at this moment. Okay, so if the signer has produced sigma and sigma, let us assume that sigma is properly available to the receiver. And for the verification algorithm also, all the inputs are given properly. All right. Now the proof, the formal proof. As I have told you, the formal proof is somehow trying to relate the breakability of the scheme to the solvability of a hard problem. Okay, so how do the formal proof is done? The formal proof is given in terms of an interaction between a challenger and an adversary. There are two characters here. One is called the challenger and another is called adversary. This adversary is a person who is capable of breaking a system. We want to show that such a fellow does not exist, but for the sake of contradiction, to demonstrate a contradiction, assume that an adversary or a forger exists. Okay? But what is that forger in the real world is going to do? How is he getting this forging ability? He is getting the forging ability because of the following information available with him. One is the public key of the person is available. And then he also may have several sample signatures. Okay, so he may use the sample signatures available with him in some way, and then finally he may be able to produce a forgery, right? Therefore, if we want to really relate the solvability of a hard problem with this forgery, what we have to do is the following. We have to give him a system. We have to give him some sample signature. Now the sample signature is not on the document that you give it to him. He may choose the message and ask the signature, because he may want the signature with some special properties in order to break. For example, he may ask, what is the signature on 1? What is the signature on 111? What is the signature on 11111? And so on. He may ask anything. You have to produce the corresponding signed document for him so that he uses them in some black box manner and finally produces the forgery for you. Therefore, you have to now first play the game. Okay? Well, the whole thing which I am saying as an adversary can be given as lemma 1, lemma 2, lemma 3 and so on, but that is somewhat dry and complex to understand. So cryptographers have found out more complicated way of explaining this, and that's what I am going to do, because eventually when you go to crypto literature, this is what you will find. Therefore, I will follow the same style. So here is the way in which the hardness is proved. First, the public parameter, the system that you are supposed to break, you give to him. And after giving the system to break, okay, he is going to ask the hash queries. Give the hash function response, whatever is the hash function, because the hash values are all used in my scheme. Yeah, hash queries. Huh? He can get? Yes. Which one? No. Well, that is a trivial instance, isn't it? Therefore, he may ask for lot of signature, and finally he should produce something which is not he has queried. Then only we say that he has accomplished the forgery. Forgery is producing something which is not produced by the owner of the system. If you simply give back what is produced by the owner of the system, that is not called forgery. Forgery is something that you have developed on your own without the involvement of this. These are all genuine signature. The signed document is available. For example, if you go to the bank, there are a lot of signed document by various users are available to the system administrator. So he has at his disposal plenty of signed document. Huh? We cannot choose. Adversary cannot choose, but here we are now taking it to the extreme of, okay, you choose, even then you will not be able to break is the argument. Which means an adversary who could not choose will be a weaker adversary, right? In fact, I am proving the impossibility for a stronger adversary. I am saying that even if I supply to the person the signature of the message of his choice, even such a person will not be able to produce a forgery. That is the contradiction I am going to show. So I will give him a long rope. I will allow him to take the signature on anything that he wants. In fact, I am going to give him polynomial number of signatures. Okay? Lot of signature sample he can take. Whatever he wants, he can take. Still, he will not be able to produce. That is the kind of a claim I am going to prove. Okay? So, here is the way in which it is proved. Hash queries are done. That is also responded. And sign oracle. Sign oracle, give me the signature on this message. And then he will produce the signature and so on. Okay? I am rushing, not because I am going to skip this detail. I am going to give the details for it. I am now showing you the way in which it works. Finally, he is going to produce a forgery. And with the forgery, we are going to demonstrate the solution. This is the outline. So I have quickly shown the outline. So given the hard problem, after a lot of, this is called the training phase. This is the simulation of the real world scenario available for a forger. So I am simulating a real world scenario. Then he is producing a forgery. Once he produces a forgery, using that I am going to solve the problem. Okay, and this mathematical exercise will demonstrate the non-existence of that forgery. If I could complete all the details of each step that I have flashed, okay, if I show how I can, what kind of a system I have given him to break, how I have constructed my hash answers, and how I am going to use his forgery to solve the hard problem, if I could show all of them, then that completes my formal proof. So that is exactly what I am going to do. The details are fairly simple. Okay? The details are absolutely simple. Only thing is you have to get used to the way in which the whole content is grasped. That's all. Okay? So here are some fundamental tricks which I am going to explain. This is there as a part of all provable security. So what do you start with? You start with what is your goal? Your goal is to use a forger to solve a hard problem. What is a forger is capable of doing? Forger is capable of doing my signature scheme, which I have shown you earlier. That's all. Now, if I want his capability to break my hard problem, I have to inject the instance of the hard problem into the system design. Then only his breaking of that system will lead to my solution. Therefore, the first step is, how do I inject the instance of the hard problem into the system design and present that, hey, you said you are capable of breaking, can you break this system? And I would give it. Okay? So here is the way in which I am giving the system. What do you mean by giving the system? Giving the public parameter. What are the public parameter? Remember, for my scheme, the public parameter are two values S1 and S2 are chosen, and S1P and S2P are the public key. So the group, the generator, and these two values are to be given to him. And when these values are given, these two are the secret keys. This is the way in which the system is designed. This is what he is going to do. The challenger will give, this is the hard problem instance, the computational Diffie-Hellman, P, AP, BP is given to him. Now the goal is to find APB, but forget the goal for the moment. So the challenger has got P, AP, BP. Now what he will give is, he will give P and he will give AP. AP he will dub as the first public key, and the public key has got two components. The second for the second component he will choose S2, multiply by S2 with P, and then construct P2. So P1 is the directly borrowed from the hard problem. P2 is S2P where S2 is known, and he will give P1, P2 is. Can you break this public key system? The adversary will say, of course I can break, but give me some sample signature. Give me the hash value answers, he would say. And that is how the training program is going to proceed. Okay? So in the training phase, all the answers are going to be perfectly given to him. What is the subtle point and what is the major challenge here? Notice the following. I do not know A or B. That is why I have printed A and B in red. I have P, I have AP, I have BP, but I don't know A and B. Can I find A or B? I cannot find A or B. So that is a discrete log problem. So no one can find A or B, but I have the value of AB, I have the value of BP without knowing A or B. So the first secret key is actually A, but that is implicitly A. Even I do not know. So I have given him a public key whose secret key I do not know. Right? I really do not know the secret key of the system, but I have given him, can you break it? And I have given him a public key of the system. Now, actually the secret key has two components. One component I know, one I do not know. Where will I face the challenge? The challenge I will face is when he says, please give me the signature of a message. The signing, if you want to produce a signature, you have to use both the secret keys. If you look into the signing algorithm, that QM value is produced with S1 and S2. But I really do not have one secret key at all. One secret key is implicitly A, I don't have that value. That is the reason why I have to simulate the signature. I have to give him something which will somehow pass the verification test. Okay, so I will do some complete mathematical jugglery to produce something which will pass the verification test, but that is not, it is a signature, but it is not produced by the signing algorithm. If you want to produce a signature using signing algorithm, you need secret keys, but I do not have actually the secret key, so I am going to do some mathematical jugglery, and that is why it is called the simulation. This person C, the challenger, is another name for the challenger is called the simulator. He is going to only simulated answers he will give, but he will give convincing answer. He will give mathematically correct answer. Therefore, mathematical properties are never violated. In the training program, for every question that is asked, mathematically correct answers will be given, and that is what the demonstration of the simulation. This simulation can be described through lemmas. Lemma 1, this response satisfies this property. Lemma 2. But instead of saying that, these people have, in cryptography, they have a very dramatic way of presenting that this is the query that is asked, this is the response that is given, and so on. Absolutely no fear. The moment I demonstrate, you can easily get a mathematical equivalence of it. You can grasp it without any difficulty. Okay. So here is the way in which, what is the hash 1 query? He is going to ask, give me the hash of one message and ym. So he will choose one ym, and he will choose an m, and then he will ask for h1 of m. Okay. What is h1 of m? Because you are not giving him the body of the hash function, you are going to use a random oracle. Okay. So the random oracle must produce a random element from the response. And here is the second clever move that I do. The second instance of the hard problem, namely BP, is injected here. I choose a random element, multiply the random element with BP. Therefore, this is a random element, and this random group element is given as a response. So notice the way in which I am producing a response. My response is produced with an injection of the second instance of the hard problem. Therefore, my hash function, the random oracle's response, has got some hidden agenda. Basically, I am supplying him the value in such a way that eventually I will be able to use his forgery if at all he produces something. Let us see how we do that later. But for the time being, the first clever step is, in the public key, I have cleverly injected one instance of the hard problem, but he will not recognize that it has got a hard problem instance injected in it. Some 2 group element is a public key, and he got 2 group element. And hash values are random element from the group, and random element from the group he will keep getting it. But each random element is actually a multiple of this BP with a random element, and so on. Okay. And the second oracle, random oracle, is very simple. You generate a random item and then respond. So QM has no special mathematical properties. Randomly choose a QM and then give it. He asks, what is H2 of MXM? You send some random number. He is asking for some other, what is H2 of M1 XM1? You generate another random number and give that as a response. Okay. So random oracle is perfectly satisfied. And here comes the last tricky part. The last tricky part is generating the sign oracle. Suppose he is asking, give me the signature on M, and he gives you a message M. Now you have to produce something which is passing the verification test. Somehow you have to fool it, cook up some value, because you cannot run the sign algorithm. To run the sign algorithm, you need both the secret keys. You do not have both the secret keys, so here is the absolutely nasty thing that you do. What you do is, you take some random number and multiply by P, the H, and call it as HM. And you select a random DM P, QM minus P1, you do this and then get YM. Then S2 is chosen by you, H is chosen by you, H by S2 you can compute, YM is computed here, and then you call it as ym, okay, and after calculating xm is like this, choosing dm like this, doing all this computation, okay, you simply give xm as xm dm, yeah, xm dm. xm is computed here, dm is chosen here. This value you give it as a response. This is the signature query. This is the computation that you do. You select some values and then you do some computation and then you give this value back to him. Will it convince him? You have done something very funny. You have not run the signing algorithm and produced this xm and dm. You have done something funny and then produced this. We are going to show that this is a perfect simulation. In other words, the values which are produced here will perfectly pass the verification algorithm, the test in verification algorithm. Because the verification algorithm is a testing for some pair of numbers whether that E is satisfying some condition. I have cooked up this value and their cancellations in such a way that the test would pass because of the bilinearity property. In bilinearity property, I can move this B here, A here, both of them I can take up. So I can make it in such a way that they cancel out the effect, and then I made this to work. So here is the very simple argument that E of xmp2 equal to, that is the verification test. The simulated signature is valid and passes the verification test. Okay, this is a straightforward arithmetic. I am not going to spend time on explaining that. That's absolutely straightforward. You can take it for granted. You don't have to know anything other than the bilinearity property and cancellation and so on. A divided by A equal to 1. That's the only thing you should know. Other than that, nothing else you have to know to convince the proof for it. Okay, let's not spend time on it. What is important is the following. If I could, without knowing the secret key, produce something convincing, is it not a forgery, you may ask? The answer is no. This is a forgery only with respect to the hash function value that I have created and so on. In general, in the real world, hash function values you cannot create. There is a body of the function which you have to use, and those values are impossible to reverse engineer by collision resistance property and other properties. Therefore, in real world you cannot produce this kind of a trick. In our mathematical argument and simulation, for the random function that I have defined, for the random oracle that I have defined, I can cook up something and play around and complete the simulation. This shows that I can give a perfect training. In other words, whatever the adversary asks, I can give the response to him. Now, adversary is equipped with all the information that he wants. Now he can produce a forgery, right? Because he is a forger and he is capable of producing a forgery, therefore he is now going to produce a forgery, and then that is what is done here. So the forgery has come. The forgery is for M star, he has produced XM star, DM star. M star is the message. For this XM star, DM star is the forgery. Okay? He has produced. All that is remaining is how to use this forgery to solve the hard problem. In other words, how do I use this to compute A, B, P? I don't know A, I don't know B. I have the knowledge of AP, I had the knowledge of BP, but now I have with me the forgery also. How do I use all of them to produce ABP? Here is the demonstration of that. So, without getting straight into the computation, the property of this bilinearity would imply this condition. So, the two things that you have to notice here are the following. The forgery of M star is XM star, DM star. XM star will have this property. Okay? XM star will have this property. Why XM star will have this property? Since it is a forgery, it is going to satisfy the bilinearity property. That means there are 4 values. These 4 values are here. both of them are multiple of the same R star. That is, xm star will be multiple of this and ym star is multiple of this. That R star is not known, it is a theoretical value. R star is not known to anybody, but because it is passing the test, some R star must exist satisfying this condition. But H1 M star ym star, H1 is where I have inserted the hard problem instance, BP is introduced. So my H1 star is H star BP and R star is multiplied. So xm star is R star, this is H1 M star ym star. Therefore my xm star is going to be like this. And here is a straightforward computation to show that my dm star is going to be like this. So the forger has produced a xm star and dm star. xm star has this property, dm star has this property. Okay. Now here is the magic or one line argument. Now C computes this value 1 by qm star, dm star is multiplied by bp, xm star is multiplied by s2 h star. So notice that bp is known, dm star is known, this dm star has come as a part of forgery, xm star has come as a part of forgery, h star is chosen by adversary. Therefore all the values here are known, therefore the delta can be computed, and delta is nothing but ABP, and that is what is demonstrated here. So dm star BP is dm star is this value, so this value is multiplied by BP. So AQM star S2R star is multiplied by BP minus S2 by H star R star H star. Now H star and H star will get cancelled. S2R star BP, S2R star BP. This is a minus sign. Therefore these two terms would vanish, and what you will have is AQM star BP, AQM star BP, and here you have QM star in the denominator. Therefore the delta which is computed here is nothing but ABP. In other words, once the forgery is done after order 1 computation, okay, I can obtain the solution of the hard problem. So if a forger exists, okay, now what is the time taken by the forger? The time taken, in fact, what is the time taken to solve the hard problem? When did you begin with the hard problem? You began with the hard problem and then you started giving the training. So in the training, polynomial number of queries are answered, polynomial number of signatures are produced, all of them are going to take polynomial time. Then the forger works in polynomial time by assumption and he produces a forgery. And after that polynomial time, here is order 1 computation, and then you have the solution to the hard problem. So from the moment I got the instance of the hard problem, I have spent polynomial time with a forger and I have obtained the solution of the hard problem, right? And this is impossible. Therefore, such a forger cannot exist. Okay? Therefore, such a forger cannot exist, and that completes the argument for this. Okay? Obviously, I have to spend some more time that I have with commercials. So what is the commercial? Now I'll tell you what is so good about this algorithm, why the award was given to this paper and all. Before this result, we did not have an algorithm which is having a proof that is reducing without what is known as Forking-Lemma. There are algorithms there were protocols that were using Forking-Lemma to arrive at the proof of the security of signature scheme. But the Forking-Lemma would always degrade the quality of the relation between the hardness of the problem and forgeability of the scheme. Okay? That is the reason why people were looking for something without Forking-Lemma. And they want one such system to design deterministic ID-based system which is useful for aggregation. Since this has led to a scheme and that was solving an open problem since 1984, one of the long-standing open problem was solved based on this is the fundamental building block, and using this building block you can see that further things are going on and so on. Therefore, there are many more things. I'm not going to say any of those things, but all I want to tell you is that this is a novel technique which has resulted in the tight reduction of the hardness of a problem to the signature scheme, and the real life implication is that even with the smaller key size, it is possible to achieve high level of security. Roughly put, this is the implication of our reduction. If 1000-bit computational Diffie-Hellman problem is hard, then the 1000-bit signature scheme also is equally hard. In the previous reduction, it is something like this. In order to match the 1000-digit Diffie-Hellman problem, you must use a signature scheme that has got 8000-bit keys. And if you are using 2 keys, it will require 16,000 bits. Imagine the complexity of the key size. The advantage of tight reduction is the degree of difficulty of the hard problem and the security parameter values of the scheme you want to implement will have a close relation. In other words, even with smaller key size, you can achieve higher degree of security. That is the major plus point of this scheme. Without Forking-Lemma, we proved by a direct reduction, and that to order 1 computation is the only extra effort which relates the degree of difficulty of hard problem and breakability or forgeability of the signature scheme. It's very tight relation. So it is as hard as computational Diffie-Hellman problem, and that is the winning point of this particular scheme. Plus the corollary and the implication and the use of this in ID-based cryptography was the additional benefits that we have got. The novelty is in this scheme. The applicability of this in other scheme to solve a long-standing open problem was the final icing on the cake. Okay, so this has appeared in IWSec, but you can also see this in public forum. We have in all cryptography, there is an IACR, International Association of Cryptology Research, and IACR.org is keeping an ePrint archive, and you can get the full version of this paper in ePrint archive. It is for anyone to log in and download the technical reports which are available in open ePrint archive. Okay, so you can put my name and digital signature, you will get all the papers, and in particular you can look at this paper as well. Okay, so I will give the title, and it will have the following. Title: Identity-based deterministic signature scheme without Forking-Lemma. With this title, if you search, you can download it. It has got all the details about the computation, model, justification, application, real-world key size. All details are available in the full version of the paper. You can take a look at it. It has also led to some interesting open problems as well, which you can pursue if this problem domain excites you. Okay, that is 1 minute left for you to ask some question. It's a very nice scenario, right, for a speaker. Speak for 1.5 hours and give the audience only 1 minute to ask questions. Highly condensed minute. Anyway, so if there are no further questions, I stop my presentation. Oh, there is a question. Wait. Yes. Huh?
Could you publish this slide somewhere along with the also?
Yeah, these slides are available with them. The full paper is also available for you to download in ePrint archive. IACR.org. IACR.org, ePrint archive. Go to this site, you can get all our publications, you can download. Okay? Thank you very much.